This is why we cannot travel at the speed of light. Imagine for a moment that you could travel at the speed of light. In barely 1 second, you would circle the Earth 7½ times. You could reach the Moon in little more than 1 second, attain Mars in a matter of minutes, and explore the nearest stars in just a few years. It would be humanity's ultimate dream come true, the key that would open the doors of the cosmos and transform us into a truly interstellar civilization. But there is one fundamental problem. The laws of the universe state that it is impossible. For millennia, human beings have gazed at the stars with awe and longing. Our ancestors created myths about gods who crossed the heavens in chariots of fire. The Greek philosophers speculated about the nature of those bright points that decorated the celestial vault. With the passing of centuries, we built more powerful telescopes and discovered that these lights were not mere divine adornments, but distant suns, complete worlds waiting to be explored. However, the more we learned about the universe, the more conscious we became of an uncomfortable truth. The cosmos is incomprehensibly vast, and we are terribly slow. The speed of light is approximately 299,792 kilometers per second. This number is not arbitrary nor negotiable. It is not simply the speed at which light travels, but the absolute speed limit of the universe itself. Nothing that possesses mass can achieve it, much less surpass it. This restriction is not technological. It is not a matter of constructing more powerful engines or more efficient fuels. It is a fundamental law of physics, as unbreakable as gravity or the conservation of energy. Before continuing, I would love to know where you are watching us from tonight. Leave your city or country in the comments, and whether you are using this video to relax before sleep or simply out of scientific curiosity. And if you haven't already done so, consider subscribing to Ciencia Nocturna, where every week we explore the deepest mysteries of the universe while accompanying you through your nights. The story of how we discovered this universal limit is fascinating in itself. For the majority of human history, we assumed that light traveled instantaneously. It seemed logical. You light a candle, and the room illuminates instantly. The sun rises, and the world is bathed in light without apparent delay. It was not until the 17th century that the Danish astronomer Ole Rømer performed observations of the moons of Jupiter and noticed discrepancies in their eclipse times. These variations depended on the distance between the Earth and Jupiter, which led him to a revolutionary conclusion. Light did not travel instantaneously. It had a finite and measurable velocity. This discovery was only the beginning. Over the following 2 centuries, scientists from all over the world refined the measurements of the speed of light with increasingly ingenious experiments. They used rotating mirrors, separated by kilometers, and all types of creative devices. But it was in 1905 when a young German physicist named Albert Einstein would forever change our understanding of what this velocity truly meant. Einstein did not just measure the speed of light, but he revealed something much deeper. This speed was a fundamental constant of the universe, and had implications that would challenge everything we thought we knew about space and time. The extraordinary thing about the speed of light limit is not only that it exists, but the consequences it has for anything that attempts to approach it. As an object accelerates and approaches this cosmic barrier, strange things begin to happen. Time begins to slow down, distances contract, and the object's mass increases dramatically. These are not minor or negligible effects. They are fundamental transformations of reality itself that become more pronounced the closer we get to that unreachable limit. Think about the spacecraft we have constructed so far. The Parker Solar Probe, one of the fastest objects ever created by humanity, reaches speeds of about 690,000 kilometers per hour. It sounds impressive, and it is from our terrestrial perspective. But when we compare it with the speed of light, we are talking about barely 0.06% of that limit. It is like comparing the pace of an ant with the speed of a supersonic jet. Even our most extraordinary achievements in space engineering are pathetically slow on the cosmic scale. Distances in space are measured in light years precisely because they are so vast that they are incomprehensible in kilometers. 1 light year is the distance that light travels in 1 year, approximately 9.5 trillion kilometers. The nearest star to us after the Sun, Proxima Centauri, is little more than 4 light years away. This means that even traveling at the speed of light, something we know is impossible, it would take us more than 4 years to get there. With our current technology, that journey would take tens of thousands of years. The center of our galaxy, the Milky Way, is about 26,000 light-years away. Andromeda, the closest large galaxy to ours, is 2.5 million light-years away, and the observable universe has a diameter of approximately 93 billion light-years. These numbers are so overwhelming that it is difficult to process them emotionally. They reveal a humbling truth. Even if we could travel at the speed of light, we would still be prisoners of a minuscule fraction of the cosmos. The vast majority of the universe would forever remain out of our reach. This limitation is not a cruel caprice of nature, but a direct consequence of how our universe is structured. Space and time are not separate and independent entities, as we believed before Einstein. They are aspects of a single entity that we call space-time, and the speed of light is the speed at which causes and effects propagate through this cosmic fabric. It is the speed of causality itself. To allow something to travel faster than light would be to allow effects to precede their causes, creating temporal paradoxes that would destroy the logical structure of the universe. So, why exactly can't we travel at the speed of light? The answer has multiple layers, each one more fascinating and disheartening than the last. It is not just a question of engineering or technology. It is not that we have yet to discover the correct fuel or the appropriate engine design. The problem is much more fundamental. The laws of physics, as we understand them, explicitly prohibit any object with mass from reaching this speed. And the reasons behind this prohibition lead us to some of the deepest and most counterintuitive concepts in all of science. Throughout this nocturnal journey, we will explore each of the obstacles that stand between us and the dream of traveling at the speed of light. We will discover why mass becomes infinite, why time stops, how much energy we would actually need, and what devastating effects we would face along the way. We will examine the theoretical solutions that some scientists have proposed and why most remain pure speculation. We will see how quantum particles seem to defy these rules and why they actually do not. And in the end, we will arrive at a deeper understanding of our place in a universe that, although infinitely fascinating, keeps us firmly confined to speeds that seem like crawling when measured against the cosmic scale. Albert Einstein did not discover the speed of light, but he did discover something much deeper, what that number really means. In 1905, while working as a clerk in a patent office in Bern, Switzerland, Einstein published a paper that would forever change our understanding of the universe. This work, titled On the Electrodynamics of Moving Bodies, introduced to the world the theory of special relativity. What Einstein proposed was so radical that even many scientists of the time resisted accepting it. However, the mathematics were irrefutable, and the theory's predictions were confirmed over and over again by subsequent experiments. Einstein's brilliance did not arise from complex experiments in laboratories equipped with cutting-edge technology. It arose from thought experiments, from imagining hypothetical situations, and taking the logic to its ultimate consequences. One of his most famous thought experiments began when he was barely 16 years old. He asked himself what he would see if he could travel riding on a beam of light. According to Newton's classical physics, he should see the beam of light frozen in space as a static electromagnetic wave. But this contradicted Maxwell's equations about electromagnetism, which did not allow the existence of stationary electromagnetic waves. This paradox haunted him for years, until he found the revolutionary answer. Einstein's solution was audacious in its simplicity. The speed of light is constant for all observers, regardless of how they are moving. This sounds innocuous at first, but its implications are devastating for our everyday intuition. If you are standing still, and I run past you, throwing a ball forward, the speed of the ball that you measure will be my speed plus the speed of the ball. This is basic common sense. But Einstein said that with light, this does not work. If I travel at half the speed of light and turn on a flashlight pointing forward, both you and I will measure that the light from that flashlight travels at exactly the same speed, 299,792 kilometers per second. The speeds do not add up. For this constancy of the speed of light to be possible, Einstein had to sacrifice something that we had considered absolute throughout the history of humanity: time. Time is not universal or absolute, as Newton assumed. Time is relative. It depends on the observer and their state of motion. Two perfectly synchronized clocks will begin to desynchronize if one of them moves at high velocity relative to the other. Space is not absolute either. Distances contract in the direction of motion when you travel at speeds close to that of light. Einstein demonstrated that space and time are not separate entities, but aspects of a unified continuum, space-time. The equations of special relativity, known as Lorentz transformations, mathematically describe how the measurements of space and time change between observers moving at different speeds. In these equations, a crucial factor appears that becomes increasingly important as velocity approaches that of light. This factor, called gamma, or the Lorentz factor, is calculated by dividing 1 by the square root of 1 minus the square of the velocity, divided by the square of the speed of light. At everyday speeds, this factor is so close to 1 that its effects are imperceptible. But as you get closer to the speed of light, this factor grows exponentially toward infinity. When you travel at 10% of the speed of light, the Lorentz factor is only 1.005. The relativistic effects are minimal, barely 0.5% of a difference. At 50% of the speed of light, the factor rises to 1.15, an already noticeable 15% difference. At 90%, the factor is 2.29, more than double. But at 99% of the speed of light, the factor reaches 7.09, and at 99.9%, it jumps to 22.36. The closer you get to that limit, the more dramatic the effects become, and when you try to reach exactly the speed of light, the Lorentz factor becomes infinite, which is the universe's mathematical way of saying, you cannot get here. Einstein also discovered the most famous equation in all of physics. Energy equals mass times the speed of light squared. This simple formula reveals a profound truth. Mass and energy are interchangeable. They are two manifestations of the same thing. An object at rest has energy simply by having mass, which we call rest energy. But when that object moves, it acquires additional energy, kinetic energy. In Newtonian physics, this kinetic energy is simply 1/2 of the mass multiplied by the velocity squared. But in relativity, the formula is different and has extraordinary consequences. According to relativity, the total energy of a moving object includes both its rest energy and its kinetic energy. and this total energy increases with the Lorentz factor. At low speeds, the Newtonian formulas work well as an approximation, but as you get closer to the speed of light, the kinetic energy does not grow simply and linearly. It grows exponentially, following that same Lorentz factor that shoots toward infinity. This means that you need more and more energy to produce increasingly smaller increments of speed. It is like running uphill on a slope that becomes progressively steeper until it turns into a vertical, infinite cliff. The implications of this are devastating for any hope of reaching the speed of light. No matter how much energy you supply to an object with mass, you will never be able to accelerate it to the speed of light, because you would need an infinite amount of energy. And the universe, although vast, does not contain infinite energy. This is not a temporary technological limitation that we can overcome with better engineers or future discoveries. It is a fundamental limitation inscribed in the very structure of space-time. The speed of light is not just fast, it is an unreachable horizon, a mathematical asymptote toward which we can approach, but never touch. The fascinating thing is that Einstein arrived at these conclusions without elaborate experiments or sophisticated equipment. He did it through the power of pure thought, rigorous logic, and mathematics. He took two simple principles: that the laws of physics are the same for all observers in uniform motion, and that the speed of light is constant for all observers. From these two postulates, he deduced a whole new physics that demolished our intuitive notions about space and time. And the most extraordinary thing is that every prediction his theory made has been confirmed experimentally with astonishing accuracy. Einstein's special relativity taught us that the universe is much stranger than we ever imagined. It showed us that time can slow down, that distances can contract, that simultaneity is relative, and that a universal speed limit exists. But Einstein did not stop there. 1 decade later, in 1915, he would publish the theory of general relativity, which incorporated gravity into the relativistic framework and revealed that space-time itself can curve and deform. This theory would open the door to even more exotic concepts such as black holes, wormholes, and the expansion of the universe itself. But before exploring those speculative possibilities, we need to understand in greater depth each of the concrete obstacles that special relativity places in our path toward the stars. The first, and perhaps the most fundamental of these obstacles, is the question of mass, because it turns out that when you try to accelerate an object to relativistic speeds, its effective mass begins to increase dramatically, and this mass increment is not a minor effect or a technical detail. It is an absolute physical barrier that makes reaching the speed of light literally impossible for anything that has mass. And that is exactly what we will explore next. Imagine you are pushing an empty shopping cart through a supermarket. It is easy. It requires almost no effort. Now imagine that the cart is completely full of heavy products. Suddenly, you need to apply much more force to move it at the same speed. This intuitive concept, that more massive objects are harder to accelerate, is something we all understand from childhood. But what special relativity tells us is that even the empty cart becomes progressively heavier as you accelerate it toward the speed of light, not because you are adding more objects to it, but because the cart's mass itself increases due to its velocity. This concept of relativistic mass was one of Einstein's most counterintuitive predictions. According to relativity, the mass of a moving object is not the same as its rest mass. As an object accelerates, its effective mass increases, multiplied by that same Lorentz factor that we mentioned before. At everyday speeds, this increase is completely negligible. A car traveling at 120 kilometers per hour has a mass barely 1 billionth greater than when it is parked. It is a change so minuscule that not even the most precise instruments could detect it. But at speeds close to the speed of light, the effect becomes dramatic and dominant. Let's consider a concrete example. Suppose you have a spacecraft with a rest mass of 1,000 metric tons, approximately the mass of the International Space Station. At normal speeds, pushing this spacecraft requires a reasonable amount of energy. But let's imagine you manage to accelerate this spacecraft to 50% of the speed of light. At that point, its effective mass would have increased to approximately 1,155 metric tons. It is not a huge change yet, only 15% more. But now, let's try to accelerate this already incredibly fast spacecraft even more. To take the spacecraft from 50% to 75% of the speed of light, its effective mass would increase from 1,155 metric tons to approximately 1,512 metric tons. The spacecraft has become 51% more massive than when it was at rest, and each additional kilogram of effective mass requires more energy to accelerate. If we persist and manage to take it to 90% of the speed of light, its effective mass would now be 2,290 metric tons. We have more than doubled the mass of the original spacecraft. And this is where things become truly impossible. When we try to accelerate this spacecraft from 90 to 95% of the speed of light, its effective mass jumps to 3,200 metric tons. From 95 to 99%, it reaches 7,089 metric tons. At 99.9%, the effective mass is 22,366 metric tons, more than 20 times its original mass. And the closer we get to the speed of light, the more pronounced this growth becomes. At 99.99%, we would be talking about more than 70,000 metric tons. At 99.999%, more than 224,000 metric tons. The progression is relentless. Each additional digit of precision that we add to the percentage multiplies the mass by approximately 3. There is no escape from this mathematical reality. As you asymptotically approach the speed of light, the effective mass grows exponentially toward infinity. And when you finally try to reach exactly 100% of the speed of light, the mass becomes literally infinite. An object with infinite mass would require infinite energy to move, and infinite energy simply does not exist in the universe. It is nature's elegant way of absolutely prohibiting any object with mass from reaching the speed of light. But here, an interesting question arises. Why can light itself travel at this speed if we cannot? The answer lies in the fundamental nature of photons, the particles that make up light. Photons have no rest mass. It is not that they have very little mass, it is that they literally have zero mass. And because they have zero mass, the Lorentz factor does not apply to them in the same way. In fact, photons can do nothing else but travel at the speed of light. From the moment they are emitted until the moment they are absorbed, they always travel at exactly 299,792 kilometers per second. Never faster, never slower, never at rest. This creates a fundamental division in the universe. There are particles with mass that must always travel slower than light, and massless particles that must always travel exactly at the speed of light. There is no middle ground, no gray area. The speed of light is not just an upper limit for objects with mass. It is an impassable barrier that divides the universe into two mutually exclusive categories. It is as if the cosmos had two separate lanes divided by an impenetrable wall, the subliminal lane where we live and the luminal lane where photons and other massless particles live. We can never change lanes. The physical reason behind this mass increment has to do with how energy and mass are related in relativity. When we accelerate an object, we are adding kinetic energy to it. But due to the equivalence between mass and energy that Einstein discovered, this additional kinetic energy manifests as an increase in the object's effective mass. The more energy we supply to it, the more massive it becomes. And the more massive it becomes, the more energy is needed to accelerate it even more. It is a vicious cycle that intensifies exponentially as we approach the speed of light. We can visualize this with an imperfect but useful analogy. Imagine you are trying to climb a mountain, but every step you take upward makes your backpack heavier. Initially, the increase in weight is imperceptible, but as you climb higher, the backpack becomes progressively heavier at an increasingly faster rate. At some point, the backpack becomes so heavy that you can no longer take another step, no matter how much force you apply. Reaching the speed of light is like trying to reach the top of a mountain whose height is infinite and whose slope becomes infinitely steep, while carrying a backpack that becomes infinitely heavy. There is simply no way to get there. Modern particle accelerators provide us with direct experimental evidence of this effect. In facilities such as the Large Hadron Collider in Switzerland, physicists accelerate protons to speeds extraordinarily close to that of light. These protons circulate through a circular tunnel, 27 kilometers in circumference, accelerated by intense electromagnetic fields. The protons reach 99.9999991% of the speed of light. At that speed, each proton has approximately 7,000 times more effective mass than when it is at rest. And despite all the energy poured into these protons, they can never reach 100%. The scientists who operate these accelerators can precisely calculate how much energy they need to supply to achieve each additional increment of speed, and their calculations perfectly match the predictions of special relativity. When they try to accelerate the protons even closer to the speed of light, they need increasingly astronomical amounts of energy to achieve increasingly minute improvements in speed. It is a direct and everyday experimental confirmation that the relativistic increase in mass is real, measurable, and absolutely insurmountable. This obstacle of infinite mass by itself would be sufficient to make travel at the speed of light impossible. But nature, as we will discover, is not content with placing only one obstacle in our path. There are multiple independent barriers, each one sufficient by itself to stop any attempt to reach this speed limit. And one of the most fascinating and disturbing of these barriers has to do with time itself, because it turns out that when you travel very fast, time literally slows down for you, and at the speed of light, time would stop completely. Time is probably the most intuitive and, at the same time, most mysterious concept in our daily experience. We all feel its constant and inexorable passage. We age, clocks advance, seasons change, and we assume that this temporal flow is universal and absolute for everyone in the universe. But Einstein taught us that this assumption is deeply wrong. Time is not a universal constant that flows uniformly for everyone. It is relative, flexible, and fundamentally depends on how fast you are moving. This phenomenon, known as time dilation, is one of the strangest and most verified consequences of special relativity. Time dilation means that a moving clock ticks more slowly when observed from a stationary frame of reference. It is not that the clock is defective or that its mechanism has slowed down. It is that time itself passes more slowly for the moving object. The faster you move, the slower time passes for you compared to someone who is stationary. At everyday speeds, this effect is so minuscule that it is completely imperceptible. But as you get closer to the speed of light, time dilation becomes dramatic, dominant, and eventually infinite. To understand how this works, let's consider the same example we used before with our spacecraft. If this spacecraft travels at 50% of the speed of light, time aboard passes approximately 15% slower than time on Earth. This means that if the astronauts traveled for what they perceive as 1 year, approximately 1 year and 2 months would have passed on Earth. The difference is noticeable, but not dramatic. However, as the speed increases, the temporal discrepancy becomes increasingly pronounced and astonishing. If the spacecraft reaches 90% of the speed of light, time aboard passes approximately 2.3 times slower. 1 year for the astronauts would be equivalent to 2 years and 3 months on Earth. At 95% of the speed of light, 1 year aboard would correspond to more than 3 Earth years. At 99%, 1 year for the travelers would be equivalent to more than 7 years at home, and at 99.9% of the speed of light, a single year of the astronaut's subjective time would correspond to more than 22 years on Earth. The people they left behind would have aged more than 2 decades, while they only experienced 12 months. This progression continues in an increasingly extreme manner the closer we get to the speed of light. At 99.99%, 1 year aboard would be equivalent to more than 70 years on Earth. At 99.999%, we would be talking about more than 224 Earth years for every subjective year. And when we try to reach exactly the speed of light, time dilation becomes infinite. Time would stop completely for the traveler. From the perspective of a photon, if we could adopt such a perspective, the journey from the Sun to the Earth is instantaneous. The 8 minutes that light takes to cover that distance are experienced only by external observers, not by the photon itself. This phenomenon is not abstract theoretical speculation. It has been verified experimentally countless times with extraordinary accuracy. One of the most elegant examples involves subatomic particles called muons. Muons are constantly created in the Earth's upper atmosphere when cosmic rays collide with air molecules. These particles are unstable and have a half-life of approximately 2 microseconds before disintegrating. At the speed muons travel, even approaching the speed of light, they should disintegrate long before reaching the Earth's surface. However, we constantly detect muons at sea level. The explanation for this apparent paradox is time dilation. The muons travel at speeds so close to that of light that time passes much more slowly for them. From our terrestrial perspective, they live much longer than 2 microseconds, long enough to complete the journey through the atmosphere. From the perspective of the muon, on the other hand, its life is still approximately 2 microseconds, but the distance it must travel has contracted due to another relativistic effect called length contraction. Both perspectives are equally valid and lead to the same observable prediction. The muons reach the surface. Relativity works perfectly. Another everyday, but less known, example of time dilation occurs with the satellites of the Global Positioning System. These satellites orbit the Earth at speeds of approximately 14,000 kilometers per hour and at altitudes where gravity is slightly weaker than on the surface. Both factors affect the passage of time. The orbital velocity causes time dilation that slows the satellite's clocks by approximately 7 microseconds per day. However, the lower gravity at that altitude causes the opposite effect, accelerating the clocks by approximately 45 microseconds per day. The net effect is that the satellite clocks advance approximately 38 microseconds faster each day than the clocks on Earth. 38 microseconds may seem insignificant, but for a system designed to provide positioning accuracy at the meter level, it is critical. Light travels approximately 30 centimeters in 1 nanosecond, so 38 microseconds of error would quickly accumulate positioning errors of several kilometers. For this reason, the engineers who designed the system must continuously adjust the satellite clocks to compensate for relativistic effects. Every time you use your phone to navigate, you are benefiting from corrections based on Einstein's theory of relativity. It is a daily reminder that these effects, although counterintuitive, are absolutely real. Time dilation also leads us to one of the most famous paradoxes of relativity, the twin paradox. Imagine you have two identical twins. One remains on Earth, while the other undertakes a space journey at a speed close to that of light toward a distant star and then returns. When the traveling twin returns home, he discovers that he has aged much less than his brother, who remained on Earth. If the journey was fast and long enough, the traveling twin could return after what were only a few years for him and find that his brother has aged decades or even died of old age. This is not a real paradox in the sense of a logical contradiction, but rather a situation that profoundly challenges our intuition. The situation is not symmetrical because the traveling twin had to accelerate, decelerate, turn around, and accelerate again to return, while the terrestrial twin remained in a constant inertial frame of reference. This asymmetry breaks the apparent symmetry of the problem and resolves the paradox. The twin who experienced the accelerations is the one who ages less, and both twins will agree on this when they meet again. Relativity consistently predicts which twin will have aged less, and there is no real contradiction. Now, what does all this have to do with our inability to reach the speed of light? The infinite time dilation at the speed of light represents another fundamental barrier, independent of the problem of infinite mass. If you could travel at exactly the speed of light, time would stop for you. You would not go through a slowed-down experience. You would literally not experience the passage of time at all. From your perspective, the journey from one end of the universe to the other would be instantaneous. But this creates deep, conceptual problems. How could you accelerate to that speed if time has stopped for you? How could you experience or measure anything? It is another way in which the universe says that this limit is unreachable for objects with mass. The combination of infinite mass and infinite time dilation forms an impenetrable double barrier. It is not that one of these effects makes it difficult to reach the speed of light. It is that both, independently, make it absolutely impossible. And we are not finished with the obstacles yet, because even if we could magically ignore these problems, we would still face the practical and devastating question of where we would get the necessary energy to perform such a feat. And when we examine the numbers involved, we discover that the figures are so astronomically large that they make impossible seem like too weak a term. Let's talk now about concrete numbers, about the real energy we would need to accelerate something to speeds close to that of light. Because it is one thing to speak in the abstract about infinite mass and time dilation, and quite another to calculate how much energy we would have to generate, store, and apply to achieve something like this. The results of these calculations are so overwhelming that they transform the theoretical impossible into something that seems beyond any practical conception. Let's explore exactly how much energy we would need and why even advanced civilizations would face insurmountable obstacles. Let's start with something relatively modest: accelerating a small 1 metric ton spacecraft to 10% of the speed of light. At this speed, the spacecraft would travel at approximately 30,000 kilometers per second, which sounds impressively fast. At that rate, we could reach Proxima Centauri in little more than 40 years. The relativistic effects at this speed are still quite small, so we can use Newtonian approximations for our calculations. The necessary kinetic energy would be approximately 5 times 10 raised to the 18 joules. To put this into perspective, that is equivalent to the energy released by more than 1,000 megatons of TNT, approximately 20 times more powerful than the largest thermonuclear bomb ever detonated. Now, let's consider accelerating that same 1 metric ton spacecraft to 50% of the speed of light. Here, the relativistic effects begin to be significant, and the required energy is not simply 25 times greater than for 10%. Due to the relativistic mass increase, we would need approximately 1.3 times 10 raised to the 20 joules. This is equivalent to approximately 30,000 megatons of TNT, or all the energy that humanity consumes in approximately 1 year, concentrated on accelerating a single object, the size of a small car. And remember, this only takes us to half the speed of light, not to the limit itself. If we try to take our 1 metric ton spacecraft to 90% of the speed of light, the numbers become truly astronomical. We would need approximately 5 times 10 raised to the 20 joules, equivalent to more than 128,000 megatons of TNT. This amount of energy is comparable to all the solar light that reaches the Earth for approximately 1 hour. We are talking about capturing and concentrating colossal amounts of energy that far exceed anything that our civilization can currently generate. And we would still be only at 90% of the speed of light, with that last 10% remaining exponentially more difficult. Now, let's consider the extreme case, accelerating our spacecraft to 99.9% of the speed of light. The necessary energy would be approximately 2 times 10 raised to the 21 joules. This is equivalent to approximately 500,000 megatons of TNT, or all the energy that the Sun radiates into space for approximately 2 hours. For a civilization like ours, which has barely begun to explore space, this amount of energy is completely out of reach. Even for a hypothetical Type II Kardashev-scale civilization, capable of harnessing all the energy of its star, sending a small spacecraft at this speed would require a significant fraction of its total energy budget. And remember that all these calculations are only for the spacecraft itself, not including the fuel. This is a critical problem because any conventional propulsion system needs to carry its own fuel, and that fuel also has mass that must be accelerated. This creates a devastating vicious cycle known as the Tsiolkovsky rocket equation. The more fuel you carry, the more total mass you have, which means you need even more fuel, which adds more mass, requiring still more fuel, and so on. At relativistic speeds, this problem becomes exponentially worse due to the relativistic mass increase. To illustrate the severity of this problem, let's consider a hypothetical scenario using the most efficient propulsion system we know, theoretically, matter, antimatter, annihilation. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy, according to Einstein's famous equation. This is the most efficient mass-to-energy conversion possible, according to known physics. There is nothing more efficient in the entire universe, and yet the numbers are prohibitive. To accelerate a 1 metric ton spacecraft to 90% of the speed of light using matter, antimatter, annihilation propulsion, you would need to carry approximately 6 metric tons of combined fuel between matter and antimatter. This might not sound terrible until you consider the practical implications. First, you need to produce and store 3 metric tons of antimatter. Antimatter is incredibly difficult to produce. Currently, all the antimatter that humanity has cumulatively produced would amount to barely a few nanograms. Producing kilograms, much less metric tons, would require monumental technological advances and astronomical amounts of energy. Second, storing antimatter is extremely challenging because any contact with normal matter results in instantaneous annihilation. You would need perfect electromagnetic containment systems that never fail under any circumstances. A single error would mean a catastrophic explosion, equivalent to thousands of nuclear bombs. But the most fundamental problem is that these calculations only cover the initial acceleration. If you want to decelerate when you reach your destination, you need approximately the same amount of energy again. And if you plan to return home, you need double that. So for a round trip, you would be talking about something like 16 metric tons of matter-antimatter fuel for a 1 metric ton spacecraft. The ratio between fuel and payload quickly becomes unmanageable, especially when you consider that all that additional fuel must also be accelerated, which requires even more fuel in a recursive calculation that quickly explodes toward impracticality. And all this is only to reach 90% of the speed of light. If we wanted to get even closer to the limit, say to 99%, the fuel requirements would multiply several times more. At 99.9%, we would be talking about dozens of metric tons of antimatter, and the closer we get to the actual speed of light, the fuel requirements grow exponentially toward infinity. It is another manifestation of the same fundamental limit. You cannot reach the speed of light because you would need infinite energy, and the universe does not provide infinite energy. Some have proposed ingenious alternatives to avoid the fuel problem. One idea is to use solar sails or laser sails, where the spacecraft does not carry its own fuel, but is pushed by radiation pressure from an external source. This eliminates the problem of the rocket equation because the spacecraft does not have to carry its own fuel. However, it presents its own formidable challenges. To accelerate a sail to significant relativistic speeds, you would need an incredibly powerful laser, operating continuously for years or decades. The energy source for that laser would have to be colossal, possibly requiring the construction of massive solar arrays in space. And once the spacecraft is far away, decelerating it becomes extremely problematic without a source of thrust at the destination. Another proposal is the Bussard ramjet, a theoretical spacecraft concept that would scoop up hydrogen from the interstellar medium and use it as fuel for nuclear fusion as it travels. In theory, this would provide unlimited fuel and allow continuous acceleration. Unfortunately, detailed calculations have shown that the interstellar medium is too tenuous for this concept to work efficiently. The aerodynamic drag of collecting the hydrogen would probably exceed the thrust generated by burning it. Furthermore, at relativistic speeds, that hydrogen would turn into lethal radiation, a problem we will explore later. The Bussard ramjet remains a fascinating, but probably impractical, idea. The crude reality is that there is no known or theoretically plausible propulsion system that can take macroscopic objects to speeds truly close to that of light, without requiring amounts of energy that defy any practical implementation. We could, with sufficiently advanced technology, perhaps reach 10 or 20% of the speed of light. That would be a monumental achievement and would open the nearby star system to exploration, although the journeys would still take decades. But truly getting close to the limit, entering that regime where relativistic effects completely dominate, remains out of reach, not only for our current civilization, but probably for any physical civilization. The energetic barrier is simply too high, too fundamental, too absolute. Let's imagine for a moment that we have somehow solved all the problems we have discussed so far. Suppose we found an almost unlimited energy source. We developed technology to manage the growing relativistic mass and built a spacecraft capable of reaching a significant fraction of the speed of light. Even in this optimistic and fantastic scenario, we would face an additional problem that could be the most lethal of all: cosmic radiation. At relativistic speeds, apparently empty space becomes a deadly battlefield, where every errant atom transforms into a devastating projectile capable of destroying any spacecraft and annihilating any crew. Interstellar space is not really empty. It contains approximately 1 hydrogen atom per cubic centimeter on average, along with traces of other elements and subatomic particles. At normal speeds, this is completely insignificant. Current space probes traverse this interstellar medium without any appreciable problem. However, as your speed approaches that of light, these innocuous atoms turn into something completely different. From the perspective of a spacecraft traveling at relativistic speeds, every hydrogen atom it encounters turns into a high-energy radiation particle that impacts with devastating force. To understand why this happens, we need to consider relative kinetic energy. When you travel at 90% of the speed of light and collide with a hydrogen atom that is essentially stationary, the collision is equivalent to being hit by that atom moving toward you at 90% of the speed of light. The kinetic energy of that collision is proportional to the square of the velocity multiplied by the relativistic mass. At relativistic speeds, this means that even the lightest particles carry colossal amounts of energy. A single proton impacting your spacecraft at 99% of the speed of light would have an energy comparable to that of a baseball pitched at high speed. All that energy concentrated at a subatomic point. Now multiply this by the number of collisions that would occur. At speeds close to light, your spacecraft would traverse approximately 1 trillion hydrogen atoms per square meter per second. Each of these atoms would strike the spacecraft's frontal hull with extreme relativistic energies. The constant bombardment would be equivalent to being under continuous fire from extremely intense cosmic rays. The spacecraft's hull would heat up rapidly to extreme temperatures due to the constant energy deposition. The materials would erode, become radioactive due to induced nuclear reactions, and eventually fail. Any electronic system would be destroyed by the penetrating radiation that would pass through even the thickest shielding. But the problem is even worse than it initially seems. Not only do you face the hydrogen atoms of the interstellar medium, but there is also the cosmic background radiation, the photons of the cosmic microwave background that fills the entire universe. In the Earth's frame of reference, these photons have very low energies corresponding to microwaves, but due to the relativistic Doppler effect, when you travel toward them at speeds close to light, these low-energy photons transform into high-energy gamma rays from your perspective. The cosmic background radiation, which is normally completely harmless, turns into a constant bath of lethal gamma rays that bombards your spacecraft from all directions forward. This phenomenon is known as the cosmic ray wall. As your speed increases, the full spectrum of electromagnetic radiation in the universe shifts toward higher energies from your perspective. Visible light turns into ultraviolet, then into X-rays, then into gamma rays. Microwaves turn into visible light, then into ultraviolet. All radiation becomes progressively more energetic and more lethal. At 99.9% of the speed of light, you would be sailing through what is essentially a gamma ray oven, so intense that it would vaporize any known material in a matter of seconds. Detailed calculations show that at speeds greater than 95% of the speed of light, the radiation dose a spacecraft would receive would be absolutely lethal to any carbon-based life form. Even with meters of lead or water shielding, the radiation would penetrate and destroy biological tissues almost instantaneously. Electronic systems would fail due to the ionizing radiation that would create cascades of errors in circuits and memory. The molecular structures of the hull materials would break down due to induced nuclear collisions. The spacecraft would literally disintegrate under the constant bombardment of extreme energy radiation. Some have proposed ingenious solutions to this problem. One idea is to place a massive magnetic shield in front of the spacecraft that would deflect the charged particles before they can impact the hull. This would work in principle for protons and other charged particles, but would require magnetic fields of extraordinary intensities extending for kilometers in front of the spacecraft. The energy needed to maintain such fields would be colossal, significantly adding to the already prohibitive energetic budget of the trip. Furthermore, magnetic fields do not deflect photons, so the problem of the cosmic gamma-ray wall would remain unresolved. Another proposal is to use a physical shield of expendable material, essentially a massive block of ice or metal mounted on the front of the spacecraft that absorbs the bombardment while gradually eroding. The problem with this approach is mass. To provide adequate protection at relativistic speeds, the shield would need to be meters thick and cover the entire frontal area of the spacecraft. This adds metric tons, or even tens of metric tons, of mass that must be accelerated along with the spacecraft, multiplying the already astronomical energy requirements that we discussed earlier. And as the shield erodes, you need to carry additional spare mass, making the problem even worse. There is also the problem of secondary radiation. When high-energy particles impact the shield or the spacecraft's hull, they do not simply stop. They create cascades of secondary particles, neutrons, mesons, additional gamma rays, and a whole host of nuclear reaction products. This secondary radiation can be, in some cases, more penetrating and more harmful than the primary radiation. So even with heavy shielding, the crew and the spacecraft systems would be exposed to significant levels of radiation. It is a problem that has no easy solution within the laws of physics as we understand them. There is another disturbing aspect of this problem that is often overlooked. At speeds extremely close to light, say 99.99% or more, even microscopic interstellar dust becomes a mortal danger. Grains of dust that would normally be invisible and harmless turn into projectiles with the kinetic energy of bombs. A single dust speck the size of 1 micron, impacting your spacecraft at that speed, would release as much energy as a small explosion, potentially perforating the hull and causing catastrophic damage. Interstellar space is full of such dust particles, making the journey at ultra-relativistic speeds not only lethal due to radiation, but also dangerous due to devastating physical impacts. The cruel irony of all this is that the faster you try to travel to reach your destination sooner, the more hostile the medium you must traverse becomes. It is as if the universe had multiple superimposed defense systems against high-speed travel. First, there is the barrier of infinite mass. Then there is the barrier of infinite energy. Then there is time dilation that distorts your experience of time. And now we discover that even if you could overcome all those barriers, space itself turns into a lethal minefield of radiation and microscopic projectiles that would make the journey virtually impossible for anything complex like a crewed spacecraft. Every additional level of speed you reach not only requires exponentially more energy, but also exponentially increases the hostile environment you must endure. The twin paradox that we mentioned earlier is only the tip of the iceberg when it comes to the strange and counterintuitive effects of high-speed travel. When you start traveling at significant relativistic speeds, you do not just experience time differently. Your complete experience of reality transforms in profound and disconcerting ways. The universe literally looks, behaves, and works differently for you than for someone who remains stationary. These effects are not illusions or tricks of perception. They are genuine transformations of the structure of space-time that you have the right to experience in your frame of reference. One of the most dramatic effects is length contraction, also known as Lorentz contraction. Just as time slows down for moving objects, distances contract in the direction of motion. From the perspective of a stationary observer, an object traveling at high speed looks physically shortened in its travel dimension. From the traveler's perspective, it is the external universe that seems to contract in the direction they are traveling toward. At moderate speeds, this effect is imperceptible, but at speeds close to light, it becomes extremely pronounced. An object traveling at 99.9% of the speed of light would have its length contracted to approximately 5% of its rest length. For a relativistic space traveler, this length contraction has profound implications. Imagine you are traveling toward Proxima Centauri, which is 4.2 light-years away, according to terrestrial measurements. If you travel at 90% of the speed of light, from your perspective, the distance to Proxima Centauri has contracted to only approximately 0.6 light-years. This means that, although observers on Earth would see your journey take a little over 4 years, you would experience the journey as taking only about 6 months of your subjective time. The combination of time dilation and length contraction makes the journey substantially shorter from your perspective than from the perspective of those you left behind. At even more extreme speeds, the effect becomes more pronounced. At 99.9% of the speed of light, the 4.2 light-years distance would contract to only approximately 0.19 light-years from your perspective, making the journey seem to take barely a few weeks of your subjective time. At 99.99%, the distance would contract to only 0.06 light-years, and the journey would seem to take only a few days. In theory, the closer you get to the speed of light, the more the distances contract until, at the mathematical limit of the speed of light itself, all distances in the direction of travel contract to zero. From the perspective of a photon, the entire universe is infinitely thin in the direction of its travel. Another fascinating effect is relativistic aberration, which dramatically changes how you see the starry sky around you. As you accelerate toward relativistic speeds, the stars in front of you seem to concentrate more and more toward a point directly ahead, while the stars to the sides and behind you shift backward. It is as if the entire universe were compressed into a bright ring in front of you. At 90% of the speed of light, almost all the visible stars in the sky would appear to be contained in a cone of only about 16 degrees in front of your spacecraft. The rest of the sky behind you would look mostly empty and dark. At even higher speeds, this cone of light would narrow even more until it became a bright point directly ahead. The relativistic Doppler effect also transforms your visual perception of the universe. The stars you are traveling toward not only look more concentrated, but their light shifts toward the blue, increasing their apparent energy. The stars would look progressively more blue and brighter the faster you travel. Conversely, any light coming from behind you shifts toward the red, losing energy. At extremely high speeds, the visible light of the stars in front of you would shift completely out of the visible spectrum into ultraviolet and X-rays, while the stars behind you would shift into infrared and microwaves, becoming essentially invisible. The universe would look fundamentally different for a relativistic traveler than for us here on Earth. There is also a related effect with simultaneity that profoundly challenges our intuition. In Newtonian physics, we assume that simultaneity is absolute. If two events occur at the same time for one observer, they occur at the same time for all observers. But relativity demonstrates that this is false. Events that are simultaneous for one observer are not necessarily simultaneous for an observer who is moving relative to the first. This effect is called the relativity of simultaneity and becomes more pronounced at higher speeds. Two events that occur at the same time from your perspective on Earth could have occurred years apart from the perspective of a relativistic traveler. This leads to paradoxical situations from our everyday perspective. Imagine you send a spacecraft to Alpha Centauri at relativistic speed, and simultaneously, from the Earth's perspective, your twin brother is born. When the spacecraft arrives at Alpha Centauri years later, according to terrestrial clocks, your brother is several years old. But from the perspective of the spacecraft pilot, due to the relativity of simultaneity, Your brother's birth might not have happened yet when the spacecraft arrived. Events that are simultaneous in one frame of reference are ordered differently in time in another frame of reference. There is no universal, absolute now that spans the entire universe. This relativity of simultaneity also implies that the concept of cause and effect must be handled with care. Special relativity preserves causality, ensuring that no event can causally influence another event separated by a spatial distance greater than what light could travel in the time between them. This defines something called the light cone. All events that could causally affect you must be within your past light cone, and all events you can affect must be within your future light cone. Events outside your light cone cannot have a causal relationship with you, no matter which frame of reference you use to describe them. The psychological experience of these effects for a relativistic traveler would probably be disorienting and profound. Imagine knowing that although only months have passed from your perspective, decades have elapsed on Earth. The people you knew have aged. The world has changed. Technology has advanced. Returning home means traveling not only through space but effectively into the future, turning you into a stranger in your own world. This is the existential price of relativistic travel. You temporarily separate yourself from your civilization of origin. Each trip displaces you further forward in the time of your home world. There are also practical considerations related to navigation and communication. At relativistic speeds, the radio signals you send toward Earth or receive from it would be enormously affected by the Doppler effect. Communications would become progressively more difficult the faster you travel. The signals would take years to arrive, and when they finally arrive, they would contain information about an increasingly distant past. A real-time conversation would be impossible. You would be essentially isolated, traveling through a universe that, from your perspective, has transformed into something almost unrecognizable compared to the everyday experience we know. All these strange and counterintuitive effects are inevitable consequences of traveling at speeds close to light. They are not failures in our understanding or limitations of our technology. They are fundamental properties of spacetime as it is structured, and while these effects might be navigable in principle, they add additional layers of complexity and challenge to the already monumental problem of reaching relativistic speeds. Travel at the speed of light is not only physically impossible, even approaching that limit so radically transforms your experience of reality that it raises deep questions about identity, continuity, and what it means to be part of a civilization. And we are not finished exploring the barriers and challenges yet, because now we must ask ourselves, are there ways to circumvent these limitations? Faced with all these apparently insurmountable barriers, theoretical physicists and science fiction enthusiasts have proposed ingenious alternatives that could, at least in principle, allow us to cross vast cosmic distances without directly violating the speed of light limit. These ideas exploit technical loopholes in the laws of physics or propose exotic manipulations of space-time itself. The most famous of these proposals is the warp drive, also known as warp impulse, popularized by science fiction, but based on real and serious physics. However, as we will discover, these apparently elegant solutions come with their own sets of fundamental problems that may be as impossible to solve as the original problem. The concept of the warp drive was mathematically formalized by the Mexican physicist Miguel Alcubierre in 1994. His idea was brilliantly ingenious. Instead of moving the spacecraft through space at superluminal speeds, why not move space itself around the spacecraft? Einstein's general relativity teaches us that spacetime can curve and deform in the presence of mass and energy. Alcubierre proposed that if you could create a bubble in spacetime that expanded the space behind your spacecraft and contracted the space in front of it, you could effectively surf on a wave of expanding and contracting spacetime. The spacecraft itself would remain stationary within its local spacetime bubble, never moving locally faster than light. But the bubble itself could move arbitrarily fast. This concept is mathematically consistent with general relativity. Alcubierre's equations describe a valid solution to Einstein's field equations. Technically, you do not violate the speed of light limit, because you are not moving through space faster than light. Space itself is moving, carrying you with it. It is a subtle but crucial distinction. The universe itself already does something similar. During cosmic inflation, in the first moments after the Big Bang, space expanded faster than the speed of light, and it continues to expand today, although at a much slower rate. So, in principle, creating a warp bubble does not violate any fundamental physical law. However, the details of the warp drive reveal monumental problems. To create the warp bubble that Alcubierre describes, you would need an exotic form of matter with negative energy density. We are not talking about antimatter, which has positive energy. We are talking about something much stranger, matter, or fields that have negative energy that repel gravitationally instead of attracting. This negative energy is necessary to create the contraction of space in front of the spacecraft. The problem is that we are not sure if such matter or fields can exist in macroscopic quantities. Quantum effects allow for temporary and very localized negative energy densities. But scaling this up to the massive quantities needed for a warp drive is completely outside our current understanding. Alcubierre's original calculations suggested that you would need an amount of negative energy equivalent to the mass energy of Jupiter to create a warp bubble capable of transporting a spacecraft the size of a starship. This is already prohibitively enormous, but subsequent work has refined these calculations. The physicist Harold White proposed modifications to Alcubierre's design that could reduce the energy requirements dramatically, potentially down to the equivalent of only a few metric tons of mass energy. However, this still requires negative energy, which remains speculative, and the amounts involved are still astronomical by any current technological standard. Furthermore, creating and maintaining this energy configuration would require technologies that we cannot even imagine how to build. There are also deep causal problems with the warp drive. Some analyses suggest that once you create a warp bubble, you would not be able to control it from within. You could not turn it on, turn it off, or steer it, because the control signals would be cut off from the interior region of the bubble to the regions where the space-time geometry is being manipulated. You would be effectively trapped inside your own bubble, unable to influence its trajectory or destination. Other analyses suggest that the bubble would accumulate high-energy particles in its front as it travels. And when you finally deactivate the warp drive, these particles would be released as a devastating burst of radiation that would vaporize anything at your destination. Solving these problems would require physics that we currently do not possess. Another theoretical proposal for traveling faster than light involves wormholes, also known as Einstein-Rosen bridges. A wormhole is essentially a tunnel through space-time that connects two distant locations. Instead of traveling the long distance through normal space, you could enter one end of the wormhole and emerge almost instantaneously at the other end, potentially light years away. Wormholes are perfectly valid solutions to the equations of general relativity, so in principle, they could exist. The problem is that traversable wormholes, those you could travel through without being destroyed again, require exotic matter with negative energy density to keep the wormhole's throat open against its natural tendency to collapse. Even if you could create or find a traversable wormhole, there are additional problems. Wormholes naturally connect regions of space-time that are at the same temporal moment. To turn a wormhole into a time machine that allows you to travel to the past, you would need to manipulate one of its ends by taking it on a high-speed journey to create a temporal difference between the mouths due to time dilation. But this opens up the possibility of causal paradoxes. You could travel to the past and prevent your own birth. Physicists have extensively debated whether nature allows such paradoxes, and many suspect that there are unknown quantum protections that prevent travel to the past that would violate causality. There is also the practical question of how you would create a wormhole in the first place. Theoretical solutions exist on paper, but we have no idea how to manipulate space-time on the scale necessary to create such structures. It would require energy concentrations comparable to those that existed in the first moments of the universe and technologies to control quantum gravity that are completely beyond our current physics. Some have speculated that advanced civilizations could harness microscopic wormholes that might form naturally in the quantum foam of spacetime and amplify them to macroscopic sizes. But this is pure speculation, built upon speculation, without any experimental or observational basis. Another idea that is occasionally proposed is the possibility of traveling through additional dimensions. String theory and some other unification theories suggest that there might be additional spatial dimensions beyond the three that we experience. These extra dimensions would be compacted or curled up at scales so small that we do not normally detect them. In principle, if you could access these additional dimensions, you could take a shortcut through normal three-dimensional space, similar to how a worm could travel through an apple instead of crawling on its surface. However, there is no experimental evidence that these additional dimensions exist, much less that they are accessible or useful for travel. The harsh reality is that all these exotic proposals, while mathematically interesting and consistent with certain aspects of theoretical physics, require conditions or materials that we do not know how to create, have never observed, and may not exist at all. They require manipulations of spacetime that are completely out of reach of any conceivable technology. They are fascinating as theoretical exercises and as inspiration for science fiction, but they do not represent practical solutions to the problem of interstellar travel. At least, not with our current understanding of physics. It is possible, though improbable, that future discoveries will reveal new aspects of reality that make some of these ideas more plausible, but based on what we know now, they remain firmly in the realm of speculation. What all these proposals have in common is that they attempt to find technical loopholes in the laws of physics rather than violating them directly. None of them truly propose moving through space faster than light in the conventional sense. All attempt to circumvent the limit by manipulating space-time itself in exotic ways. This reflects how fundamental and absolute the speed of light limit is. Even the boldest and most creative speculations of theoretical physicists do not attempt to break this rule directly. They only attempt to find ways to go around it. And so far, all these ways to go around it seem to require physics or technologies that are so far from our current capacity that they might as well be magic. The speed of light limit remains unbroken, challenging, and apparently absolute in any physically realistic scenario. In the search for ways to overcome the speed of light limit, some theoretical physicists have speculated about the existence of hypothetical particles that would naturally travel faster than light. These particles, called tachyons, represent one of the most fascinating and problematic ideas in theoretical physics. If they existed, they would completely transform our understanding of causality and time. However, as we will discover, the very existence of tachyons would create paradoxes so profound that most physicists believe they simply cannot exist in our universe. They are mathematically possible, but physically absurd, a crucial distinction in theoretical physics. The concept of tachyons arises from the same equations of special relativity that prohibit normal particles from reaching the speed of light. Recall that a particle's energy depends on its rest mass and its velocity according to the relativistic transformations. For normal particles with positive mass, energy grows toward infinity as velocity approaches that of light from below. But the mathematics also allows for solutions where particles would have imaginary mass, a mathematical concept where mass squared is negative. For these hypothetical particles, the equations indicate that they would always travel faster than light and could never decelerate to the speed of light or below it. The word tachyon comes from the Greek times tachys asterisk, meaning fast. They were formally proposed for the first time in 1967 by the physicist Gerald Feinberg as a theoretical possibility consistent with special relativity. Tachyons would have extraordinarily strange properties. As a tachyon loses energy, it would accelerate instead of decelerate. The lowest speed it could reach would be infinite, which would occur when its energy was zero. To decelerate a tachyon to the speed of light, you would need to supply it with infinite energy, which is the exact mirror of the problem we face with normal particles. The universe would be divided into three velocity regions: subluminal particles that always travel slower than light, luminal particles like photons that always travel exactly at the speed of light, and tachyons that always travel faster than light. If tachyons existed, and we could detect and interact with them, the consequences for causality would be devastating. A tachyon, traveling from one point to another faster than light could, from certain frames of reference, appear to travel backward in time. This is not a calculation error or a peculiarity of the mathematical notation. It is a direct consequence of how relativity handles simultaneity. If you could send information using tachyons, you could send messages to your own past. You could receive an answer to a question before formulating it. You could be warned about events before they occur and prevent the causes of those events, creating irresolvable logical paradoxes. The most famous paradox associated with tachyons is the tachyon telephone paradox. Imagine you build a tachyon-based communication system that can send signals faster than light between two spacecraft traveling away from each other at high velocity. Spacecraft A sends a tachyon message to spacecraft B, which, from A's perspective, travels forward in time, but from B's perspective, it could have arrived before being sent. If B immediately responds with another tachyon message, that message could arrive at A before A sent the original message. This creates a closed causal loop, where the effect precedes the cause, violating one of the most fundamental principles of physics and logic itself. To visualize how problematic this would be, consider the following scenario. You have a button that, when pressed, sends a tachyon message to a device in the past that automatically destroys the button before you can press it. If you press the button, the message is sent. The button is destroyed, and you never press the button. But if you never press the button, no message is sent. The button is not destroyed, and you press the button. It is a perfect logical contradiction, with no possible resolution. We call this the grandfather paradox in its simplest form. You travel to the past and kill yourself before you traveled in time, which prevents you from having traveled, which means you did not kill yourself, which means you did travel, and so on, in an infinite loop of contradiction. Physicists have proposed several possible resolutions to these tachyon paradoxes. One possibility is that the universe simply conspires to prevent any use of tachyons that would create a causal paradox. Perhaps the laws of physics, when fully understood, contain still unknown protections that make it impossible to create paradoxical situations. Another possibility involves parallel universes, or branching timelines, where causal paradoxes are resolved by creating alternative realities. But these solutions introduce their own conceptual problems and are not supported by experimental evidence. The simplest explanation, and the one that most physicists favor, is that tachyons simply do not exist. There is no experimental evidence of tachyon existence. A particle traveling faster than light has never been detected in any experiment. Physicists have actively searched for tachyons in cosmic rays, in particle accelerator collisions, and in various other contexts where they might manifest if they existed. All these searches have come back negative. Furthermore, quantum field theory, our most successful framework for understanding fundamental particles, suggests that tachyons would correspond to instabilities in the quantum vacuum. If they existed, the vacuum of space would be unstable and would rapidly decay, something we clearly do not observe. The vacuum is remarkably stable, and this is indirect but convincing evidence against the existence of tachyons. There are also thermodynamic considerations. Tachyons, if they existed and could interact with normal matter, would allow violations of the second law of thermodynamics. You could use tachyon signals to create perpetual motion machines or reduce the entropy of closed systems, both prohibited by fundamental laws of physics. Thermodynamics is one of the most robust and experimentally verified theories in all of science, and any particle that violates it must be regarded with extreme skepticism. The consistency of thermodynamics with all other known physical laws strongly suggests that tachyons cannot be part of our physical universe. Reports occasionally surface in the scientific press of experiments that appear to show particles or signals traveling faster than light. The most famous recent example was in 2011, when the Opera experiment reported that neutrinos traveling from Switzerland to Italy seemed to arrive 60 nanoseconds earlier than they should if they traveled at the speed of light. This result caused great excitement and controversy, but it was eventually discovered to be caused by an experimental error, a loose fiber optic cable, and a poorly synchronized clock. Once these errors were corrected, the neutrinos traveled at exactly the expected speed, consistent with traveling at the speed of light, or slightly below. This episode illustrates how careful we must be when interpreting apparently anomalous experimental results. The lesson of tachyons is that just because something is mathematically possible does not mean it is physically real. The equations can allow for solutions that correspond to impossible or meaningless situations. Tachyons are a perfect example of this. They are a mathematically valid solution to the equations of relativity, but they create logical and physical problems so severe that they almost certainly do not exist in nature. They serve as a reminder that physics is not just mathematics. It is mathematics connected to physical reality through observations and experiments. And physical reality, as far as we can determine, does not include particles that travel faster than light. This is another nail in the coffin of our hopes of overcoming the speed of light limit. Not only is it impossible for us to accelerate to that speed, but even the hypothetical particles that would naturally travel faster than light seem to be impossible for fundamental reasons related to causality and the logical consistency of the universe. Every possible route we explore towards superluminal travel seems to be blocked by nature. However, there is one last aspect of physics that we must examine, one that at first glance seems to challenge the speed of light limit, but which upon closer examination actually confirms it. The strange world of quantum mechanics. Quantum mechanics is the domain of the extremely small, where the rules of the game seem completely different from those we experience in our daily lives. In this microscopic realm, particles can be in multiple places simultaneously. They can pass through impenetrable barriers, and they can be connected instantaneously across vast distances. This last phenomenon, known as quantum entanglement, has led many to wonder if it could provide a way to send information faster than light. The short answer is no. But the explanation of why not is fascinating and reveals how even the strange quantum world respects the fundamental speed limit of the universe. Quantum entanglement is one of the most disconcerting and counterintuitive aspects of quantum mechanics. When two particles become entangled, their quantum properties become correlated in a way that has no classical analog. If you measure the spin of one entangled particle and find it pointing up, you instantaneously know that the spin of its partner points down, no matter how far apart the particles are separated. This instantaneous correlation persists even if the particles are separated by light years. Einstein called this spooky action at a distance, and it deeply disturbed him because it seemed to violate locality, the idea that objects are only directly influenced by their immediate surroundings. For decades, physicists debated whether entanglement truly implied some type of instantaneous communication between particles, or if it was simply that the particles shared predetermined information from the moment of their entanglement. This debate was resolved by a series of brilliant experiments based on Bell's inequalities, starting in the 1970s and continuing to the present. These experiments demonstrated conclusively that quantum entanglement is real and genuine. Entangled particles really are connected in a way that transcends spatial separation. There is no predetermined hidden information. The correlations are genuinely instantaneous. This seems to directly challenge the speed of light limit. How can a particle instantaneously know what happened to its partner light years away? The resolution of this apparent paradox is subtle but crucial. Although the correlations between entangled particles are instantaneous, you cannot use this entanglement to transmit information faster than light. When you measure an entangled particle, you get an apparently random result, spin up or spin down, with 50% probability. Only when you compare your measurements with those of someone who measured the partner particle do you discover the correlation. But to make that comparison, you need to communicate through conventional channels that are limited by the speed of light. There is no way to force your particle to have a particular result that transmits specific information to the remote location. To understand why this is so, imagine you have a pair of entangled quantum dice. When you roll your die, you get an apparently random number between 1 and 6. Your friend light years away rolls their entangled die and also gets an apparently random result. But when you finally compare your results after years of waiting, while the light signals cross the distance between you, you discover that your numbers always added up to 7. The correlation is perfect and was established instantaneously at the moment you rolled your die. However, you could not use this to send a message because you cannot control what number your die obtains. You can only observe it. Your friend sees a random sequence of numbers and cannot know what pattern to look for until they receive your light message. This is the no-signaling principle in quantum mechanics, and it is a direct consequence of the mathematical structure of quantum theory. Any attempt to use entanglement to send information faster than light violates this principle and turns out to be impossible. Physicists have extensively explored all possible loopholes and traps, and all proposed schemes for quantum superluminal communication have failed for fundamental reasons. Quantum entanglement provides correlations faster than light, but not communication faster than light. It is a critical distinction that completely respects special relativity, while allowing the strange non-local effects of quantum mechanics. There is another quantum phenomenon that is sometimes misinterpreted as allowing superluminal effects: quantum tunneling. Quantum particles can pass through barriers that would be completely impenetrable according to classical physics. This is a purely quantum effect with no analog in our everyday experience. Some experiments have seemed to suggest that particles passing through barriers by tunneling do so faster than light, appearing on the other side earlier than they should, according to the speed of light. However, careful analyses have shown that no information or energy is actually transmitted faster than light during tunneling. Tunneling time is a complicated concept that does not correspond to a simple velocity of the particle crossing the barrier. Quantum mechanics also introduces Heisenberg's uncertainty principle, which states that you cannot simultaneously know the position and momentum of a particle with arbitrary precision. This has interesting consequences for discussions about velocity. At quantum scales, the very notion of a particle having a defined trajectory with a specific velocity at every moment becomes problematic. Particles exist in superpositions of multiple states until they are measured. However, even with all this quantum strangeness, when you calculate the average speed at which information or energy propagates in quantum systems, it always respects the speed of light limit. Quantum strangeness never gives you a free pass to violate relativity. In fact, one of the great triumphs of 20th century physics was the successful reconciliation of quantum mechanics and special relativity in a framework called quantum field theory. This theory, which includes the standard model of particle physics, combines the principles of both theories into a consistent mathematical framework. Quantum field theory absolutely respects the speed of light limit. All interactions between particles propagate through force, carrying particles like photons, gluons, and W and Z bosons, all of which travel at the speed of light or less. There is no mechanism in quantum field theory for the transmission of information or energy faster than light. It is remarkable how completely nature respects this speed limit. We could imagine a universe where quantum mechanics allowed some type of instantaneous communication, or where particles could occasionally exceed the speed of light in special circumstances. But our universe is not like that. Every experiment, every observation, every successful theory points to the same conclusion. The speed of light is an absolute and inviolable limit. Even in the strange quantum realm, where so many of our classical intuitions fail, this limit remains intact. It is as if the very structure of reality were designed to preserve causality and prevent temporal paradoxes at all costs. There is a deep philosophical aspect to all this. Quantum entanglement shows us that the universe is fundamentally non-local in ways we could not have anticipated. Particles separated by vast distances are genuinely connected. However, this non-locality is carefully structured to never allow the transmission of information faster than light. It is as if the universe was showing us that reality is stranger and more interconnected than we thought, but carefully maintaining the boundaries that prevent logical paradoxes. This combination of quantum strangeness with absolute respect for relativistic limits is one of the most beautiful and mysterious characteristics of our universe. The final message of quantum mechanics in relation to our topic is clear. Even in the realm where the rules are strangest and least intuitive, the speed of light limit remains unbroken. There are no quantum loopholes we can exploit to travel or communicate faster than light. Quantum strangeness is profound and real, but it is completely reconciled with relativity. Both theories, which describe such different aspects of reality, converge on this fundamental truth. 300,000 kilometers per second is not just fast, it is the absolute limit of the speed of causality in our universe. And with this understanding, we must finally confront what all this means for us as a species and for our place in the cosmos. After exploring all the physical obstacles, the theoretical barriers, and the possible escape routes, we finally arrive at a truth that is both humbling and profound. We cannot travel at the speed of light, and very probably We will never be able to get close enough to that limit to make a significant difference in our ability to explore the universe beyond our immediate cosmic neighborhood. This limitation is not temporal or technological. It is not something we will solve with enough ingenuity or enough resources. It is a fundamental restriction inscribed in the very structure of space-time. And accepting this reality forces us to fundamentally reconsider what it means to be an intelligent species in a cosmos so vast that it defies all human comprehension. Let's consider the practical implications of this limitation for the future of humanity. Our galaxy, the Milky Way, is approximately 100,000 light-years in diameter. This means that even traveling at the speed of light, something we know is impossible, it would take 100,000 years to cross it from one end to the other. With realistic technology that could perhaps reach 10% of the speed of light, that journey would take 1 million years. The Andromeda Galaxy, our closest neighbor, is 2.5 million light-years away. Even at the speed of light, getting there would take 2.5 million years. With realistic technology, we would be talking about 25 million years or more. These figures are not just large, they are incomprehensible on a human scale. The observable universe contains approximately 2 trillion galaxies, each with hundreds of billions of stars. The vast majority of these galaxies are so far away that their light has traveled for billions of years to reach us. Many are so distant that due to the accelerating expansion of the universe, we will never be able to reach them no matter how long we travel, because they are moving away from us faster than the speed of light, due to the expansion of space itself. This creates a cosmological horizon, a finite bubble beyond which the universe is permanently inaccessible to us. We are confined, not only by our inability to travel at the speed of light, but also by the expanding geometry of the cosmos itself. Even within our own galaxy, the volume of space that we could realistically explore is tiny. The nearest stars, those within a few light-years, are countable on the fingers of both hands: Proxima Centauri, Alpha Centauri A and B, Barnard's star, Wolf 359, Lalande 21185, and a few more. These are the only stars that we could reach with journeys that would take decades instead of centuries or millennia. And when we examine these stars, most are dim red dwarfs with no obviously habitable planets. The probability of finding intelligent life or worlds truly similar to Earth in this handful of systems is low. The universe has given us an extremely small cosmic neighborhood. This realization has profound implications for the Fermi paradox, the question of why we have not detected evidence of advanced extraterrestrial civilizations if the universe is so vast and ancient. One possible answer is that all civilizations, no matter how advanced, face the same fundamental limitations as we do. Perhaps the speed of light is not just our limit, but a universal limit that no civilization can overcome. If this is the case, then the distances between stars are such formidable barriers that even civilizations, millions of years more advanced than us, remain confined to relatively small regions of their galaxies. The cosmos could be full of civilizations, each one trapped in its own bubble of accessible space, unable to communicate or interact across the vast distances that separate them. There are also deep philosophical implications. For most of human history, we assumed that with enough time and effort, any physical destination was reachable. The oceans seemed vast and impossible to cross, but we built ships. The skies seemed unreachable, but we built airplanes and rockets. We landed on the moon and sent probes to the confines of our solar system. Every barrier we encountered was eventually overcome, but the speed of light is different. It is not a technological barrier that we can overcome with better engineering. It is a fundamental limit of reality itself. There are places in the universe that, according to the laws of physics as we understand them, we will never be able to reach, no matter how long we wait or how advanced our technology becomes. This limitation forces us to confront our cosmic insignificance in a direct way. We are a young species on a small planet, orbiting a common star in the suburbs of a typical galaxy. The universe is incomprehensibly larger than us, and most of it is permanently out of our reach. We are not the center of the cosmos, and we will never dominate more than an infinitesimal fraction of it. This is a humbling truth, but there is also a strange beauty in it. The universe is vaster, more mysterious, and more sublime than we will ever be able to fully experience. There will always be frontiers beyond our reach, mysteries we will never solve, wonders we will never witness directly. But the story does not end in despair. Although we cannot travel at the speed of light, we are not completely immobile. We can, with sufficient technological development, reach speeds that are a significant fraction of the speed of light. 10 or 20% of the speed of light is not impossible, just incredibly difficult. At those speeds, the nearby star system becomes accessible within human lifetimes or generations. Proxima Centauri could be only 20 or 40 years away. Dozens of star systems could be within a century of travel. This does not give us the galaxy, but it gives us a cosmic neighborhood in which we could, in principle, establish a presence. There is also the possibility of generational ships, where multiple generations of humans live and die during a journey of centuries or millennia toward distant destinations. Or we could develop hibernation or suspension technologies that allow travelers to sleep for most of the journey. We could send artificial intelligences or robotic probes that do not require the same survival conditions as biological humans. None of these solutions overcome the speed of light limit, but all represent ways in which we could, over very long periods of time, gradually expand our presence beyond Earth. We will not conquer the galaxy, but we could sow small outposts of terrestrial life and consciousness in some of the closest star systems. There is also deep value in simply observing and understanding the universe from our position. We do not need to travel to distant galaxies to study them. The light that reaches us carries information about their composition, their dynamics, their history. Space telescopes allow us to observe the universe in wavelengths that our eyes cannot see. We detect gravitational waves from black hole collisions billions of light years away. We study the cosmic background radiation that tells us about the universe when it was only 380,000 years old. Although we will never visit most of the cosmos, we can observe it, measure it, and develop a deep understanding of its workings. In a sense, this is as valuable as physical travel. The acceptance of our limitations does not mean the surrender of our ambitions. It means honestly recognizing the limits that nature imposes and working creatively within those limits. It means valuing our solar system, which, although small on a cosmic scale, contains vast resources and the potential to sustain human civilization for eons. It means appreciating the rarity and preciousness of Earth, possibly the only world within light years where life has flourished to produce consciousness and intelligence. It means accepting that we are a local species in a vast universe, and that is okay. Our smallness does not diminish our value or the importance of our lives and experiences. Consider subscribing to Ciencia Nocturna to continue exploring these mysteries of the cosmos with us every week. It would be an honor to have you in this community of nocturnal, curious minds. The speed of light limit is final and absolute. We cannot overcome it. We cannot evade it. We cannot find real shortcuts. This truth defines our destiny as a species as much as our biology or our history. We are slow travelers in a fast and vast universe, but within these restrictions, there is still room for wonder, discovery, exploration, and meaning. The cosmos may be largely inaccessible, but the portion we can reach and understand is rich enough to occupy us for our entire existence as a species. And perhaps, ultimately, it is not about how much of the universe we can conquer, but how deeply we can appreciate and understand the marvelous reality in which we find ourselves. Good night, and may your dreams take you to places that the laws of physics could never reach.